Hello. Uh, Welcome everyone to today's 10th session on chemical engineering thermodynamics. Okay, before starting a small introduction, myself Prasil Kapadia and currently I am Prime Minister's Research Fellow at Department of Chemical Engineering, IIT Bombay. In our research group, we are basically working on molecular simulations and statistical thermodynamics, lignocellulosic biomass, and something similar that we are studying here, vapor liquid equilibria and reaction equilibria that we are differently applying. I have completed my BTech from SVNIT Surat in 2019. Then I have worked in Reliance Industries Limited at Jamnagar for a year. After that, I have completed my master's from IIT Kharagpur. Then I'm currently pursuing my PhD from IIT Bombay. Okay, so in today's session, in so many previous classes we are discussing on. First we started with non-ideality in vapor phase, then we studied vapor liquid equilibrium, and we studied first ideal solutions. Then we went from ideal solutions to non-ideal solutions, and we introduced one term activity coefficient for non-ideal solutions. Now, yes, in that case, we have studied how to deal with non-ideal solutions. Okay, so for Raoult's law, in case of non-ideal solutions for low to moderate pressures, we see that it is Y into P is equal to X gamma P set. That is what we studied, and we found so many models like Van Laar model, 2 suffix Margules model, Wilson equation, NRTL model, Unified model to find out activity coefficient. Now, after all this, using all this method, we can generate so many XY data or XX data. So it is important to know that if that data is thermodynamically consistent or not. Okay, so that consistency is checked by using Gibbs-Duhem equation. So in terms of partial molar property, it is summation of I from all components I is equal to 1 to total C components. It is Ni dmi bar is equal to 0 when we are dealing with solutions, and it is summation Ni dmi bar excess is equal to 0 when we are dealing with excess properties. Okay, so these are used to calculate the unknown properties from known ones in absence of complete experimental data. So this we will see here that when uh, we can calculate various properties. If it is n1 dm1 bar plus n2 dm2 bar is equal to 0. So if I know the one property, I can calculate other property if I don't have experimental data for that other property. That is the one application of this equation. And the second application is we can check for the thermodynamic consistency of the data if experimental data available for a directly measured partial molar property for each component over a range of composition. So these are the applications of this equation. Okay, so in the last class, I will show you. We have derived Gibbs-Duhem equation. Sorry, not this one. In the last class, we have derived Gibbs-Duhem equation in terms of activity coefficient. So this is the equation, or this is the way we have derived the equation. So we started with this SEDT minus VEDP plus this summation xi dRT ln gamma I is equal to 0. And from that we find out this equation, Gibbs-Duhem equation in terms of activity coefficient, that is Hxs by T into dt minus Vxs into dP plus R into T summation xi d ln gamma I should be is equal to 0. This is what we found out. Now, if we use that equation, sorry, yeah. So now if we use that equation, sorry. Uh-huh. So this equation He by T dt minus Ve dP plus RT summation I is equal to 1 to total components Xi dl and gamma is equal to 0. So at constant temperature and pressure conditions, these both term will be 0. So we will only be left with summation I Xi dl and gamma I is equal to 0. And from that we have this equation x1 dln gamma 1 by dx1 is equal to x2 dln gamma 2 by dx2. Okay, this is what we found out in last class. So how can I use this equation to check the consistency? So the simplest method of testing is to estimate the slope of ln gamma 1 versus x1 and ln gamma 2 versus x2. So if I see from this here, I have this equation x1 del ln gamma 1 by del x1 at constant temperature pressure is equal to x2 del ln gamma 2 by del x2 at temperature pressure. Okay, and this can be put into the following form when I replace x2 by 1 minus x1 and dx2 by minus dx1. These also we have studied in the last class. If we see here, so this we have derived. Yeah. X1 dln gamma 1 by x1 is equal to minus x. There is a mistake here. I'm sorry for that. X1 dln gamma 1 by dx1 should be is equal to it is correct. X1 dln gamma 1 by x1 is equal to x2 dln gamma 2 by dx2. Now we know that when we are dealing with binary system, x1 plus x2 is equal to 1. So dx1 plus dx2 is equal to 0. So I can replace dx2 with minus of dx1. So this is what it is done here. dx2 is replaced with minus of dx1 and x2 is replaced with 1 minus x1. So the plot of logarithm of activity coefficients against mole fraction x1 of component 1 in a binary solution as shown in this figure and measure the slopes of the tangents to the resulting curves at any selected composition. Ln gamma 1 by x1. So this ln gamma 1, ln gamma versus x1, where this is for ln gamma 1 and this is for ln gamma 2, and we are plotting with respect to x1. Okay, so for any point, if I draw the tangent, so that will give me the slope of that particular curve. Correct. So what they are writing is we have to plot ln gamma 1 versus x1, ln gamma 2 versus x1, and we have to find the slope from the tangents. Now, this equation tells us that if Gibbs-Duhem equation is satisfied, both slopes must have opposite signs, correct? So what did we find? x1 dln gamma 1 by dx1 is equal to minus x2 dln gamma 2 by dx1. So slopes should be of opposite side. And if it is satisfied reasonably well, then data is consistent at the selected composition. For a complete test, the slopes determined at each compositions are substituted, and this is satisfied or not, we can calculate. Okay, so one very important thing we should know is that the slope of ln gamma 1 versus x1 and ln gamma 2 versus x2 should be opposite. Okay, so if it is not first point, if it is not opposite, then our data is not thermodynamically consistent. If data x1 into this slope is equal to x2 into or minus x2 into del ln gamma 2 by del x1, if it is satisfied or not. If the both criteria are satisfied, then we can say that the data is thermodynamically consistent. Okay, consistent. So what we know? We know that if one of the ln gamma curve has a maximum at a certain concentration, the other curve should have minimum at the same composition. This is what we know. Then the second point is if there is no maximum or minimum point, then both curve must be positive or both curve must be negative over the entire range. Or in other words, if one component has gamma value always greater than unity and no maximum, the other component, the gamma value for the other component must likewise be greater than unity. Okay, so yeah. So if we see this plot, first plot, ln gamma versus x1. So here we see that both the plots, they are having opposite curves, opposite slopes. and there is no minima or maxima here. So this, by looking, we can see that this looks like consistent. Now, second point is this. This is ln gamma 1 versus x1, ln gamma 2 versus x2. Just by looking at, we know that if ln gamma 1 is maximum, ln gamma 2 at same composition should be minimum. So by looking, we say that this seems thermodynamically consistent. Now, if I am looking at this third curve, so we know that ln gamma 1 versus x1. So here it is maxima is here. So at same composition, I should have minima, but I am not having minima at same composition. It is slightly shifted. So we can say that at this point, thermodynamic consistency is not maintained. So this data is not thermodynamically consistent. If this or this, we don't know which one. Maybe it should be maxima here or it should be minima corresponding to this point. So we can say that this figure C, the data is not thermodynamically consistent. And if we see at figure D, so both curves, those are having the same nature, both are decreasing. So this is also not possible because the curves should have opposite values of slope, and here the slopes are similar or similar nature for the both the curves. So this data D is also not thermodynamically consistent. Okay. So we know that for this figure B, the plots of consistent data, this represent plots of consistent data because maxima, minima, and C and D, those are not thermodynamically consistent. Those are thermodynamically inconsistent data. For this C, we know that there is a maximum on one curve and minimum on the other, but they are shown at different compositions. So this is not something valid. And here we see that slopes have the same sign, and that's why thermodynamically this data is inaccurate and it is not consistent. Okay. So we first, what we need to do, we need to plot ln gamma 1 versus x1, ln gamma 1, gamma 2 versus x1, and we need to plot them. So the slopes must have opposite signs. Okay. If Gibbs-Duhem equation is to be satisfied at some constant temperature pressure, then slopes must have to be opposite signs. Okay. And then this ln gamma, if one of the ln gamma curve has a maximum at certain concentration, then the other curve should have minimum at the same composition. Okay. So this is what it was about thermodynamic consistency using ln gamma 1 versus ln gamma 2. Using this ln gamma 1 by x1 versus ln gamma 1, ln gamma 1 versus x1, and ln gamma 2 versus x1. Okay. But now in reality, we know that this is the curve that is shown. Okay. So if we don't have a proper point, let's say one point is here, one point is here, it's not forming exactly a good curve, then we can say that in that cases, finding of slope will be very difficult, and those slopes may not be accurate. In general also, this slope method, it cannot be very accurate, and it can be difficult to find out slopes at each points. And the other thing is experimental data, always it is not required that always we are going to get this kind of proper curve. So if experimental data points are not properly forming a curve, but those are scattered, then it is not easy to find the slopes. So there is better method which is called integral or area test method, which was proposed by Redlick and Kister, and simultaneously proposed by Harrington. This all Redlick-Kister and Harrington, they independently propose this method. So if we see this method, so we know that this equation, okay, I will see it here. We know that G by RT is equal to summation I xi ln gamma I. This equation we know. So what can I write? I can write that G by RT for a binary mixture. I can write that x1 ln gamma 1 plus x2 ln gamma 2. G by RT is equal to x1 ln gamma 1 plus x2 ln gamma 2. Let's say I want to differentiate this G by RT is equal to x1 ln gamma 1 plus x2 ln gamma 2 equation with respect to x1. Okay, so we see that d by dx1 of G by RT is equal to, now let's say I'm keeping ln gamma 1 constant. So differentiation of x1 with respect to x1 is 1. So we are just left with ln gamma 1 plus let's say x1 I am keeping constant. So differentiation of ln gamma 1 with respect to x1 will be d ln gamma 1 by dx1 plus, now let's say I'm keeping ln gamma 2 constant and I am differentiating x2 with respect to x1. So it is dx2 by dx1 plus I am keeping x2 constant and I am differentiating ln gamma 2 with respect to x1, that is d ln gamma 2 by dx1. Now the fact we know that is x1 plus x2 should be is equal to 1. So differential of x1 plus differential of x2 should be is equal to 0. So dx2 should be is equal to minus dx1. So dx2 by dx1 is minus 1. So what I can write, d by dx1 of g by rt is equal to ln gamma 1. This term is minus 1. So I can write ln gamma 1 minus ln gamma 2 plus x1 dln gamma 1 by dx1 plus x2 dln gamma 2 by dx1. Okay, now when we are dealing with constant temperature and pressure, so from the Gibbs-Duhem equation, we know that this term should be equal to 0. x1 dln gamma 1 by dx1 should be is equal to x2 dln gamma 2 by dx2. So this term should be equal to 0. So we are only left with d by dx1 of g by rt is ln gamma 1 minus ln gamma 2. So if I am integrating this from x1 is equal to 0 to x1 is equal to 1, so I can write differential of g by rt at x1 is equal to 0, lower limit to higher limit x1 is equal to 1. To this ln gamma 1 minus ln gamma 2, ln a minus ln b, I can write it down as ln a by b. So it is ln gamma 1 by gamma 2. So which is starting from x1 is equal to 0 to x1 is equal to 1. Okay. Now we know that when x1 is equal to 0, so it is a pure component system with x2 is equal to 1. So when we are dealing with pure component system, there is no excess property. So g by rt should be is equal to 0 when I am putting my limit x1 is equal to 0. My second limit x1 is equal to 1. So when x1 is equal to 1, my it is a pure component 1 system. Okay, so in that case also it should be 0 here, not 1. So g by rt should be is equal to 0. So what we are left with? We are left with is integration 0 to 1 ln gamma 1 by gamma 2 into dx1 should be is equal to 0. I just keep x1 here and I try to integrate the equation. So I find that ln gamma 1 by integration of 0 to 1 for entire composition range ln gamma 1 by gamma 2 dx1 should be is equal to 0. So what does this mean? This means that when I am plotting ln gamma 1 by gamma 2 versus x1, and when I am finding the area under the curve, that should be is equal to 0. If that is satisfied, then we can say that our data is thermodynamically consistent. Okay, so this is what it is derived here, that integration 0 to 1 ln gamma 1 by gamma 2 dx1 should be is equal to 0. So from the experimental values of activity coefficient, ln gamma 1 by gamma 2 values are calculated and plotted against x1 taken on x-axis, correct? The net area of the diagram should equal to 0 if the data are thermodynamically consistent. That is, the area above the x-axis will be equal to the area below as it is shown. So area above x-axis should be equal to area below x-axis. If that is the case, then we can say that the total summation is going to be equal to 0. Okay. Yes. So area above x-axis. So what do we know when I'm going to sum up the area? So what is going to happen? It will not be always exactly equal to 0, but it will be, let's say it is 0.001. It is 0 minus 0.001 like that. So in that case, can we say that it is consistent or not? So for that, this we are going to use that mode of area above x-axis minus mode of area below x-axis. So I'm taking absolute value. Divide by mode of area above x-axis plus mode of area below x-axis. That is what I'm going to find out. Okay. So if this number, overall mode of area above x-axis minus area below x-axis minus area above x-axis plus area below x-axis, if this summation, if this particular value, if it is going to be, wait, I have not written what the criteria is. So if that is less than or equal to 0.02, then we can say that our data is thermodynamically consistent based on this ln gamma 1 by gamma 2 versus x1 plot. So we need to find both area above x-axis, area below x-axis. And if I find out the difference divided by total area, so I know that if it is less than 0.02, then I can say that my data is thermodynamically consistent. There are various other methods also available to check the consistency of the data, but that we are not going to use. Okay, so yeah, so this here we have a assumption that temperature and pressure are kept constant throughout the system. But let's say temperature and pressure are not constant. Then what do we need to do? We need to consider these terms. This He by T dt VEdP terms we need to consider. Okay. So we have this formula ln gamma 1 by gamma 2 dx1 is equal to 0 to 1 He by RT square dt minus 0 to 1 VE by dP. So at x1 is equal to 0, what is the temperature? And at x1 is equal to 1, what is the temperature? Similarly, when x1 is equal to 0, what is the pressure? And x1 is equal to 1, what is the pressure? That will be our lower and higher limit. Okay, if this term is equal to 0, V by dP, then there is excess volume is equal to 0. If this He by RT square dt is equal to 0, so we say that there is no enthalpy of mixing. So when does this happen? V is equal to 0 and H is equal to 0 when we are dealing with ideal solution in which chemically similar components should be present. Okay, so we see that there are various ln gamma 1 by gamma 2 versus x1. So we see that there is this one kind of curve that we get. Then this is straight line. So straight line of things are obtained for ideal gas when we are dealing with similar sizes like hexane and toluene. Then we are getting a curve in case of this benzene and isooctane. Then there can be one complex curve where we have one point of inflection. So this kind of curves are obtained for highly complex mixture, let's say for ethanol and methyl cyclohexane. Okay, so this is what all about thermodynamic consistency. Okay, now the first thing when we started, we see that we can use this to calculate the unknown properties from the known ones in absence of complete experimental data. Okay, so let's say let's try to take one small problem from here. So we see that we are given that ln gamma 1 is equal to ax2 square plus bx2 cubed plus cx2 raised to 4, where a, b, and c are concentration independent parameters. So if this is ln gamma 1, what can be my ln gamma 2? Okay, so in last class, we had this derived this equation that ln gamma 1 del ln gamma 1 by del x1 is equal to x2 by x1 del ln gamma 2 by del x2. Okay, so what do I need to do? First, I need to satisfy this equation, I need to find out del ln gamma 1 by del x1. Okay, so we have ln gamma 2 is equal to minus 0 to 1 x1 by x2 d ln gamma 1, ln gamma 1. Just a minute, I'm getting confused. Um, Yeah. So what will be my ln gamma 2? Ln gamma 2 will be, if I am differentiating this equation, it will be 2a, um, 2a x2 with respect to x2, it will be 2a x2 and x2 is uh, just a minute, 2a x2, yes, it is 2a x2 plus 3b x2 square plus 4c x2 cube. If I am differentiating del d ln gamma 1 by dx2. So see this equation we have. what did we do? We wrote here in terms of x2. So I can also write here in terms of x2. So dln gamma 1 by dx2, it will be here negative sign only. Okay, so that is the only thing. So it is just this equation but written in some different form. Okay, so now if I am integrating this from, I am this into dx2. Now we know that dx2 is equal to minus dx1. So it is just minus sign coming out dx1, and I am writing x2 in terms of x1s. So I can directly integrate, correct? So 2a x1 will be integrated as x1 square by 2. Here we will have to apply chain rule, or we can just do x1 square by 2 minus x1 square as x1 cube by 3. Similarly, this also I need to expand. So when I am doing this and I am expanding this, I can find this kind of relation. So here what we are learning that if I am knowing the expression of ln gamma 1, I can directly find out the expression of ln gamma 2. So see, this thing we have done for this Margul two parameter Margul equation. We had done this. We had this ln gamma 1 is equal to a x2 square. So we found out dln gamma 1 by dx1, and we just applied the integration and we find out ln gamma 2 is equal to a x1 square. So similarly, not a straightforward thing. We are given some complex relation, that is a x2 square plus b x2 cube plus c x2 raised to 4. So in this case, we will have a different or slightly complex integration. Okay, so that is what we have done. Now there is one more problem, that the following data gives the composition versus total pressure for the system chloroform ethyl alcohol at 328 Kelvin. Okay, so chloroform ethyl alcohol, when chloroform concentration is 0.0331, P is 40.84 kilopascal, and when it is 0.9652, it is 84.88 kilopascal. Now vapor pressures of chloroform and acetone, there is some mistake in the book itself. Either it is acetone or or ethyl alcohol. So component 1 and 2 are 328 kilopascal. 328 Kelvin are 82.35 kilopascal and 370.30 kilopascal. So we are supposed to find the Margul's constants from Margul equation. So this is the Margul equation. Ln gamma 1 is equal to x2 square a plus 2 times b minus a x1. Ln gamma 2 is equal to x1 square into b plus 2 times a minus b into x1 x2. Correct? A is equal to ln gamma 1 infinite, B is equal to ln gamma 2 infinite, where gamma 1, gamma 2 infinite are infinite dilution activity coefficient. When x1 tends to 0, this is ln gamma 1 infinite. When x1 tends to 1 or x2 tends to 0, it is ln gamma 2 infinite. And when we replace P is equal to P1 plus P2, x1 gamma 1 P1 set plus x2, what is P? P is equal to x1 gamma 1 P1 set plus x2 gamma 2 P2 set. So from there I have written gamma 1. Okay. Gamma 1 approaches 1. As gamma 1 approaches 1, gamma 2 becomes unity. So this is what it is done. So here gamma 2 is 1 put, and here gamma 1 we have put 1. Correct? And when we put this value, so we see that this is x1 tending to 0 and this is x1 tending to 1. So in this case, we have two equations, gamma 1, and similarly we can have equation when we make the subject to gamma 2, and we know that when x1 x2 tending to 1, so gamma 2 is tending to 1, and when x2 is tending to 0, gamma 2, when x1 is tending to 1, gamma 1 is tending to 1. So that is what it is taken here. So gamma 1 infinite is equal to this when x1 tends to 0, x2 tends to 1, so this is 1. And then we have just put the value and we have found out the constants A and B. So what is the strength of this method to find out this? So when we know that one data is x1 tends to 0, another data is x1 tends to 1. So we have limiting condition, and in that case we know that when x1 is tending to 0, so other component is we can consider pure component, and in that case gamma 2 tends to 1, and when x1 tends to 1, so in that case we can say that gamma 1 is equal to 1. Okay, so like that we can find out the gamma 1 infinite, gamma 2 infinite, and from there we can find out when we put gamma 1, gamma 2 here and we solve these two equations simultaneously, we can find out the values of A and B. Okay. Now this we are not going to see. Okay. So let's quickly recap what we did as of now. So we used to, from Gibbs-Duhem equation, we used to calculate unknown properties from known ones in absence of complete experimental data. Okay. And we can check thermodynamic consistency of the data that we are having. So for that, we have this x1 dln gamma 1 by dx1 is equal to minus x2 dln gamma 2 by dx1. So we know that slopes of ln gamma 1 versus x1 and ln gamma 2 versus x1 should be of opposite signs. And if one has minima, the other hand should have maxima at the same points. And both the this can't have the same slope, or nature, they both slopes should be opposite. So that is what is required. So this method is also difficult and it is not very accurate because it is difficult to find out slopes at each point. And when experimental data points are not, we can connect through lines, but those points are scattered, then it is not easy to find out the slopes. Then we have this area test method. When we see that uh, integration 0 to 1 ln gamma 1 by gamma 2. So area of ln gamma 1 by gamma 2 versus x1, when we sum it up, it should come out to be 0. Okay. So if these two things are there, we can say that our data is thermodynamically consistent. Okay, so now let's try to move ahead. So here we know that ln gamma 1 by gamma 2 from Redlich-Kister equation, we have this kind of formula. So when there is a straight line for this equation, we found that ln gamma 1 by gamma 2 versus x1 is a straight line. Okay, so when it is a straight line, when can I get this a straight line? When all these constants b, c, d are 0, we have only constant a. We are also getting this kind of curve. So when can we get curve? We can when we have c and d term 0, but we have a and b. And when we are getting more and more complex curves like this point of inflection here, so we need to consider more and more constants in the equation. Okay, so that is the benefit of Redlich-Kister equation, that it can easily, we can see that if our slope is straight line or curve or some complex curve, based on that constants, we can see if it's a straight line, then this constant need to be equal to 0. Okay, so now let's try to move ahead. There is one very important concept that is called is partially miscible systems and completely miscible, partially immiscible or completely immiscible systems. Okay, so let's first try to have a look at partially miscible system. So this is this is how the curve looks like, temperature composition diagram for partially miscible systems. So what are we having here? We are having one vapor phase and two liquid phase. La, Lb, it is in equilibrium with vapor phase. Okay. So figure 8.21 shows the temperature composition diagram for a partially miscible system at constant total pressure, constant P, pressure is kept constant. Okay, points A and B indicate the, here there is pure A, so this is my boiling point of A, and when it is equal to x1 is equal to 0, it is pure B, so this point is my boiling point of B. So points A and B indicate the boiling points of pure liquids A and B at this pressure. A binary system consisting of two liquid phases and vapor phases univariant according to the phase rule. By fixing the pressure, the system is completely defined. Okay. So we have C minus, if I do C minus P plus 2, so we have two components, three phases and C minus P plus 2. So we are left with 1. So we have to fix something that uh, constant pressure we are fixing. Okay. So we see that from this curve, we see that there is this point where all three are coexisting. So that temperature is called T star. The states of three phases in equilibrium line on horizontal line at T star, the three phase composition temperature. So this is the temperature at which three phases can coexist. So point C and D, they represent this C and D, they represent saturated liquid phase for A and B. Saturated liquid phases, and point E, it is a vapor phase. Okay. Now let's try to talk below E. What is there below E? So below T star, below, not below E, sorry, below T star. So T star is where three phase coexist. So below T star, we see that system is entirely in liquid phase. So here it is a pure liquid B, pure liquid A, and there is LaLB. So below T star, the system is entirely liquid. It may exist as a homogeneous system or heterogeneous system consisting of two saturated liquid phases, homogeneous or heterogeneous system, depending on its overall composition. If the overall composition of the mixture lies within the region bounded by the curves FC, GD, below T star, the mixture cannot exist as a single phase. Okay. Within the region bounded by this FC and GD below temperature T star, the mixture cannot exist as a single phase. So here it is not a single phase. It separates into two saturated liquid phases. LA, A reach phase represented by line GD. Here we have A reach and here we have B reach. So GD represented, LA represented by the curve GD, and B reach LB represented by the curve FC. The compositions of these phases are determined by the intersection of a horizontal line corresponding to the temperature of the system and the curves, this GD and FC. Correct? Now, let's try to have a look at from here and let's try to understand it from here. So before going, I forgot to have a look at this delta G versus X1 curve. Just give me a minute. I'm so sorry. Yes. So we have delta G versus X1. So for any system, we know that delta G at constant temperature pressure should be less than 0. It should reduce, and when delta G is equal to 0, we know that the system is in equilibrium. So if we see this curve, so this equation, where does it go? This dg of at constant temperature pressure less than is equal to 0. This provides criteria that must satisfied by any single phase that is stable with respect to the alternate, that it split into two phases. It requires that it gives energy of an equilibrium state be the minimum value with respect to all possible changes at given temperature and pressure. Okay. So thus, for example, when mixing of two liquids occurs at constant TNP, the total Gibbs free energy must decrease because the mixed state must be the one of the lower Gibbs free energy. So here we see that Gibbs free energy is only reducing, but here we see that there is some increasing then decreasing. So this alpha and beta, those are two phases. Okay. So delta G listen. Okay. So we see that Gibbs energy change of mixing must always be negative, and plot of G versus X1 for a binary uh, system must appear as shown by one of the curves of 12.13. Okay. So for one it is reducing and for other it is also reducing. Or for overall composition from x1 is equal to 0 to 1, it looks like this. Okay. With respect to curve 2, however, there is a further consideration. If when mixing occurs, a system can achieve a lower value of Gibbs free energy by forming two phases than by forming a single phase. So here we see that um, this. So instead of forming one phase, it is forming two phases and it is lowering the Gibbs free energy. Okay, so this is in fact the situation represented between points alpha and points beta that represents the overall values of G for the range of states consisting of two phases of composition x1 alpha and x1 beta in various proportions. Okay, thus the solid curve line this zone between alpha and beta, they cannot represent the stable phases with respect to the phase splitting. This equilibrium states between alpha and beta consist of two phases. Okay, so we know that this d square of delta G by dx1 square should be greater than 0 for minimum. At fixed temperature and pressure, a single phase binary mixture is stable if delta G and its first and second derivatives are continuous functions of x1 and second derivative is positive. Okay. So this d square by d square dx1 square with respect to delta G should be greater than 0 and d square dx1 square of delta G as RT is always positive, so that should also be greater than 0. So this requirement has a number of consequences. So I know that delta G by RT x1 ln gamma 1 plus x2 ln gamma 2 plus remaining G access by RT term. So if I'm differentiating this with respect to x1, so I will have this. We have just checked ln gamma 1 minus ln x1 minus ln x2 is the term. And we know that for the stability, this d square G by RT by dx1 square should be greater than minus 1 upon x1 x2. This is for two phase composition. Okay. So I forgot to cover this first. So now let's have a look again at this two phase region. So here we have this T star. So T star is three phase region. So below T star we have homogeneous or heterogeneous liquid phase. Homogeneous meaning single liquid phase or heterogeneous meaning two liquid phases. And above T star there is single liquid phase, single vapor phase, and one liquid phase in equilibrium with vapor phase and other liquid phase in equilibrium with vapor phase. So okay, so when I am starting from the point K and when I am decreasing the pressure, so what is going to happen? I am going to convert from vapor phase to liquid phase. Okay, so there will be one first dew appearing and further reducing in temperature, vapor liquid will be in equilibrium. This liquid phase with vapor will be in equilibrium. And further reduction of temperature, we will have pure liquid beta phase. Similarly, let's say if I am starting from some point here. So it all depends on the composition where we are starting. So if I am starting from here and if I am reducing the temperature, so I will reach into this alpha vapor, alpha V equilibrium phase, and further reduction, I can reach to single liquid phase. Okay. So let's try to read out and understand what they are saying. This is what is written in book. So see, in region alpha, the system is a single liquid, reach in species 2, correct? Here if we see alpha, x1 is equal to 0, so x2 is equal to 1. So when alpha is equal to, when we are in region alpha, so it is reach in single phase and it is reach in system or species 2. In region beta, it is a single liquid. In region beta, it is a single liquid reach in species 1. In region alpha V, liquid and vapor are in equilibrium. This alpha V, liquid and vapor are in equilibrium. The states of the individual phases fall on lines AC and AE. So this AC, liquid line, AE, vapor line, and in between we have liquid vapor equilibrium. Correct? Similarly, this beta V region, liquid vapor equilibrium is there. This line BE, it is vapor, and line BD, it is a liquid. Correct? Below the three phase temperature T star, so this is three-phase temperature T star. So below that it is entirely liquid, either homogeneous or heterogeneous liquids. Okay. Okay, so this is what it was written. When a vapor is cooled at constant pressure, it follows a path represented on figure 12.15 by a vertical line. It depends on from where we are starting. So if we start from here, it will follow this path. If we are starting from here, it will follow this path. Okay. Several such lines are shown. If one starts from point K, if I am starting from point K, so it is going to reach at this beta V equilibrium region and then single beta phase. Okay. So first, the vapor first reaches its dew point at line B, correct? First, it will reach at this dew point line B, then and then its bubble point line BD, and in between we have vapor liquid equilibrium, correct, where the condensation into single liquid beta phase beta is complete. This is the same process that takes place when species are completely miscible. Okay, if one starts at point N, so what is going to happen at point N? It is in vapor phase, right? When we are starting in point N and when we are trying to reduce the temperature, what we are getting, we are directly getting into three phase line. So see, if one starts at point and no condensation of vapor occurs until temperature T star is reached, then condensation occurs entirely at this temperature, producing the two liquid phases represented by lines C and points C and D. Correct? If one starts at some intermediate point M. Okay, so if I'm starting at some intermediate point M, the process is combination of two just described. So after the dew point is reached, the vapor tracing the along the line is B. So it will be first this dew curve, then vapor liquid equilibrium beta V. Okay, and then it will be directly converted into B is in equilibrium with liquid tracing along path BD is BD. Correct? However, at temperature T star, vapor phase is at point E. So all remaining condensation occurs at this temperature, producing two liquids of points C and D. Okay, so if we are here, I can have one C and one D here. Okay. So similarly, uh, we have done this at one constant pressure. Now let's say I'm increasing my pressure from P1 to P2 to P3 to P4. So what is the effect of increasing pressure? So this figure 12.15 is drawn for a single constant pressure equilibrium phase compositions, and hence the locations of the lines change with pressure, but the general nature of the diagram is the same. Nature is going to be same, but it is going to change with increase in pressure. For most systems, species become more soluble in one another as temperature increases, as indicated by this CG and DH lines. Okay. So this kind of diagram are drawn for various pressures. So it looks like this. Okay. If this diagram is drawn for successively higher pressures, the corresponding three-phase equilibrium temperatures increases, correct? This three-phase equilibrium temperature is E, it is going to increase. This T star is going to increase. Okay. And lines CG and DH extend further and further until they meet at the liquid-liquid consolid point M. As shown by this. This is my liquid-liquid consolid point. As the pressure increases, the line CD that is getting narrowing down. So if I'm increasing pressure, this region is getting smaller and smaller and smaller. Okay, until point M, it diminishes into a differential length. For still higher pressures, let's say P4, and the temperature is above the critical solution temperature, and there is a single liquid phase. This diagram represents two phase vapor liquid equilibrium, and it has the form of 12.90 that we are not going to. This similarly looks like some minimum boiling as a drop curve. Okay, so here what we need to know, we first need to know that delta G should be less than 0, and according to that we can have single phase, or it can have delta G less than 0 by forming two liquid phases. Okay, then we had a look at this vapor liquid equilibrium curve. where extreme points are pure liquid with x1 tends to 0, and here it is x1 tends to 1 pure liquids, and here it is pure vapor. Then it is alpha V, beta V equilibrium. This is three phase composition line. This is T star. Below T star we have only liquid phase available, and when we are increasing the pressure of the system, this CD line is going to reduce and reduce and reduce, and we are going to get at one point consolute point where it disappears. Okay, it diminishes to a differential length. Okay, so similar to TXY, this is a PXY diagram. Okay, that we are not going to discuss, but it looks something like this. Now, when we now we will see with two immiscible liquids how two immiscible liquids form the phases. Okay, so this is the diagram for two immiscible or two completely immiscible systems. Okay, so A and B, those are not miscible in each other. So there is no pure A. A and B are immiscible. Yes, A and B. This is TXY, this is PXY. Let's try to understand this first. So the phase diagram for a completely immiscible system is shown in this figure. So this diagram is a special case of figure that occurring when two liquid phases LA and LB are the pure liquids A and B respectively. So in earlier case what we had seen, we had additional to this, we had these things, pure A and B phases, correct? But A and B, those are completely immiscible in this case. So consider a binary mixture of two immiscible liquids having an overall composition represented by point M. Okay, when this mixture is, so these are not going to be miscible. So this A, B are completely immiscible. So what is going to happen when I'm going to increase the temperature? When this mixture is heated, its temperature increases along the line Mn. Okay, each component line Mn. For all the temperatures up to point N, each component exerts its full vapor pressure as its partial pressure in the vapor phase, correct? When temperature T star corresponding to point N is reached, the sum of the vapor pressures becomes equal to the corresponding surrounding pressure, and system cannot exist entirely in liquid phase, and that's why vapor is getting produced. Now based on this our composition region, as we have started from here, so we will have B more. Correct. This is L XA tends to 0 line this time. So we will be reaching B. So this is LB V and this is LA V. So B will be B LB will be in equilibrium with vapor phase. When temperature T star, this we have seen. T star is therefore known as three phase temperature. The composition of the vapor in equilibrium with pure liquid at the three phase temperature is given by point E. Okay. The corresponding vapor composition will be this at this line. Okay, since there are three phases and two components present according to the phase rule, the number of degrees of freedom is 1. C minus P plus 2, we have two components. C is equal to 2, phases 3, LA, LB and V. So C 2 minus 3 plus 2. Sorry, three phases. Just a minute, I'm sorry, I made a mistake. Three phases and two components. So 2 minus C minus P, just a minute. 2 minus 3 plus 2. So we are only left with 1 degree of freedom. C is 2, phase is 3 and degree plus 2. So 2 minus 3 plus 2, that gives us 1. So it means that when pressure is fixed, the system is completely defined. So we need to fix only one constant, that is pressure, and we are doing this at constant pressure. The three-phase temperature and the equilibrium vapor composition get automatically fixed by specifying the pressure in such a way that this sum pressure is equal to PA set plus PB set. Okay. Now on further addition of heat, what is going to happen? The temperature remain constant as T star and more vapor of same composition as given by point E is formed. This continues till one of the components disappears in the liquid and the systems becomes two-phase mixture, either LAV or LBV, depending on the initial composition. Okay, now let us consider the cooling. Let's say I'm starting from point J and I'm going to reach at point K. Now let us consider the cooling of the vapor of initial composition and temperature indicated by a point J. When the temperature is lowered, the corresponding point K, this point K, the vapor pressure of pure liquid B will be equal to its partial pressure, okay? And pure B gets condensed and the vapor composition changes along the line, this KE line. This line, according to this line, it is going to vapor composition. If I this here, this line will be my vapor line and this will be my liquid line. Okay, so it is going to vapor line is going to change according to that. So we'll have LAV or LBV depending on our initial composition. Okay, now I don't know if they have described about P phase. Okay, so this is what all about this VLLE system. So we can write P star is equal to this thing P1 set plus P2 set, correct? Now this along this AE line, I can write that X1 gamma 1 P1 set is equal to Y1 into P. So I can write Y1 is equal to P1 set by P as X1 tends to 1. And similarly, for this curve AB, I can write P2 set is equal to Y2 into P. So Y2 star will be equal to P2 by P and Y1 will be equal to 1 minus P2 set by P. Okay. So this was all about three-phase VLLE diagram. This is slightly complex, but this part is just for understanding that this kind of complex system exist in reality. Okay. Okay. So now we are left with one more interesting topic that we have learned about all this vapor liquid equilibrium, liquid liquid equilibrium, vapor liquid liquid equilibrium. So what are the applications of these things? So first thing I need to show you is okay. So in distillation. So what is happening in distillation? So we know that distillation is a technique of preferential separation of more volatile component from less volatile component in feed solution by partially vaporizing feed followed by its condensation. Okay. So whatever is the more volatile compound, it will be reach in distillate, and whatever is less volatile compound, it will be reach in bottoms. Okay. The vapor produced is richer in more volatile component, and distribution of components in two phases is governed by vapor liquid equilibrium relationship. That is what we learned, that how to obtain vapor liquid equilibrium. Okay, so here we enter the feed, we preheat the feed, and then it is sent to this column. Now based on the equilibrium relationship, we will have distillate and bottoms composition. So this is the basic principle of distillation. So difference in volatility of components are needed to separate. Components are used when we are going to separate the components. So what is it? It is basically one is in vapor phase, one is in liquid phase. So that is nothing but simply vapor liquid equilibrium. Now, the second thing is, yeah, so this kind of XY diagram we have generated, and these diagrams are really useful. This XY diagram, this XY curve is used. This is our equilibrium curve. So based on that, we find the number of trays and we assume that we have attained equilibrium at each tray. But that is not the reality. So that's why we use some Murphy efficiency, point efficiency terms to correct that. Okay. Because vapor and liquid to have the equilibrium, that should have proper contact available with them. Now, and this relative volatility also we have studied. Now, the second important thing is where we have liquid-liquid equilibrium. So what is liquid-liquid? Where do we use liquid-liquid equilibrium? That is basically called liquid-liquid extraction or just extraction. So mass transfer between two immiscible liquid phases, we are doing it. Okay. So in liquid-liquid equilibrium, so liquid-liquid extraction, it is a mass transfer operation in which a solution is brought into intimate contact with a second immiscible or slightly miscible liquid. In reality, there is no completely immiscible phases. There are slightly miscibility between both the phases. So feed solution, it is brought in intimate contact with second immiscible or slightly miscible liquid in order to achieve the transfer of solute from feed to solvent. Okay. So the two liquid phases that have different densities are then separated. Okay. So let's say I'm having one component. So let's say I'm having one component. Okay, let's follow this nomenclature only. Okay, let's take this example only. That extraction of penicillin. So that is done by using some suitable solvent such as butyl acetate. So let's say I'm having penicillin in uh, some compound, let's say penicillin is some C. So I need to extract penicillin from C. So what I will do, I will I will contact it with some another component which is butyl acetate, which is also liquid and which is immiscible with this C. So what is going to happen, based on the concentration, based on the chemical potential gradient, penicillin is going to get transferred into butyl acetate phase. Okay, so this is the basic this is the example to understand liquid-liquid extraction. Okay, so two phases. So what is required, that that solvent phase, that should not be miscible in feed phase, but there are always slight miscibility of solvent into feed phase. So that should be very less. So this is liquid-liquid equilibrium. So what do? We first bring the feed and solvent into intimate contact by dispersing one phase into other as a droplets or in any other ways. Then what we do, allow it to settle, and then we will have two phases. One is extract phase, that is solvent rich phase, and another is raffinate phase, and both phases will have different densities. Now removal and recovery of solute from extract phase in a relatively pure form, we can use distillation, evaporation or crystallization, something. Then removal and recovery of solvent from each phase, usually by distillation. Okay. And this liquid-liquid extraction is basically used when we are willing to separate a component whose those are having uh, similar number of or similar boiling point, close boiling points. So in that case, we will require extremely large number of distillation trays. Then separation of heat sensitive materials. I cannot heat penicillin, else it's not going to work. Then similarly for recovery of non-volatile solutes. So if non-volatile solute is in little quantity in some large volatile solvent, in large volatile, let's say non-volatile solute A is in highly volatile component B, then it doesn't make any sense to vaporize very large quantity of B just to get a small amount of non-volatile solute. So in that case also, It is used in most application is in dilute solution and removal of organics from aqueous solution. Example is phenol, removal of phenol from aqueous waste using butyl acetate or MIBK. MIBK is considered as one of the very fine solvent which always works for extraction. Methyl isobutyl ketone. So this is what similar we are also working. Okay, so this kind of when okay, so in distillation we were having one liquid phase and one vapor phase. So there were only two components. So we have XY diagram, but here it is liquid extraction. So we have three phases: solute, solvent, and feed. So for that, so we should have a ternary diagram. It looks something like this kind of ternary diagram. So this represents A, this represents B, this represents C. So based on this, we can find out the concentrations. So this is one phase region and this is two phase region. Okay. So this G1 and H1, they represents the two liquid phases in equilibrium. G1 is richer in carrier, raffinate. H1 is richer in solvent. And further, when we connect these two, that is called a tie line. Okay. And there can be infinite number of such tie lines present here. Okay. So this was all about liquid-liquid extraction. Liquid-liquid extraction is considered more complex because it is we are not dealing with one liquid, one vapor. We are dealing with three liquid phases. So that is difficult. Now, there is one more thing. These terms we are not going to study. Yeah, we are going to now have a look at first absorption. Okay, so what is gas absorption? So it is similar operation. It is an operation in which a gas mixture is contacted with a liquid for the purpose of preferentially dissolving one or more components of the gas. Let's say I have very standard example, the removal of H2S from natural gas using solvent. So I am having a natural gas which is containing H2S. So if I can use some solvent which can dissolve H2S within it, so I can get pure natural gas from it. So that is called this absorption operation. So gas absorption is an operation in which a gas mixture is contacted with a liquid for the purposes of preferentially dissolving one or more components of the gas. The insoluble component present in the gas which is not absorbed is called the carrier gas, which is the pure what we are getting after absorption. Okay, an intimate contact between gas and liquid is achieved in a suitable equipment or device known as a like a PET column, tray tower, spray tower, or anything. Okay, some examples are absorption of oxygen from air in the vast expanse of water on the surface of earth keeps the aquatic creature alive. This is the practical example where oxygen is absorbed from air in water for the aquatic creatures. That's how uh, they get oxygen in water. Now desorption. Let's say what did I do? I had a gas and I dissolved some component in the liquid. Now what do I need to do? I need to purify the liquid and I need to reuse it. So the reverse of absorption is called desorption or stripping. The loaded solvent which is with the solute dissolved in it, leaving the bottom of the absorber is subjected to the desorption. By desorption, dissolved gas is recovered from a solution for further use and to regenerate the solvent. The regenerated solvent is recycled to the absorber. So one practical example is this absorption of CO2. So the absorption of CO2 in is an important operation in the production of synthesis gas in an ammonia plant. So an aqueous solution of alkanol amine is commonly used. The CO2 loaded amine solution leaving the absorption column is stripped of the dissolved CO2 by using open stream in stripping column, and the recovered CO2 is sent to some another operation, let's say some urea plant, and the regenerated or lean solvent which may have traces left of CO2, it will not be 100% separation, so some amount of CO2 will always be there, so that is sent back to the, it is recycled and it is sent back to the absorption unit. Okay. So this is all about absorption when we are dealing with liquid vapor. This is something I do need right now. Kevin Narayan also doing it. Okay, so if we see here, absorption, difference in solubility of gases constituents in contacting liquid phase, that is the basic principle of absorption. Now there is one more operation, that is adsorption. AD, not AB. So if we look at adsorption, so what is adsorption? So adsorption, it is defined as a selective concentration or retention of one or more components of a mixture on the solid surface. So adsorption is basically with solid liquid, or it can be solid gas mass transfer. Adsorption and reverse of adsorption is called leaching. So that is not we are going to adsorption. Correct, the selective transfer of some of the molecules of a mixture to the surface or into the bulk of the solid liquid. No, sorry. Reverse of adsorption is not called sorption. It is somewhere mentioned. Okay, so adsorption can be physical, chemical. That is not what we need to know right now. So this kind of adsorption curve, partial pressure versus percentage removal. Then these are some hysteresis that when we are doing adsorption and when we are doing desorption, it does not follow the same path. So why does this happen? This happens because of the shape of the openings to the capillaries and pores of the solid, or of complex phenomena of wetting of the solid that is occurring by adsorbate. So, but one thing is adsorption will have more partial pressure than desorption, and this is always going to happen. And there are adsorption isotherms, Langmuir isotherm, BET isotherms. I don't remember the name. Freundlich isotherm, correct? BET, this Bronner, ML, Taylor equation. These various isotherms are available. There are type 1, type 2, type 3. Various kinds of adsorption isotherms are available. Okay, so this is all about liquid. When we are dealing with distillation, it is liquid, vapor liquid. So we are contacting liquid and vapor phases derived from the same source, heating. Then absorption, leaching, or absorption is gas liquid. Leaching is solid liquid. Extraction is liquid. Gas stripping, it is reverse of absorption, that is liquid gas. And adsorption, it can be solid gas or solid liquid. So what is there in case of distillation? We need minimum of two components, right? In extraction, we need minimum of three components. Okay. In case of distillation, we express the concentration in terms of mole fractions. In case of absorption, we express the concentration in terms of mole ratios, which is I have written it here down. You can see it very well. I don't know if I have written it or not, but it is expressed in terms of mole ratios, because we need straight line, and that straight line is generally obtained from mole ratios. Yeah, okay. So, so how do we perform this operation? We first create a two-phase system or three-phase system, then we allow mass transfer operation, and then we separate these phases. So everywhere, if you see liquid, vapor, solid liquid, so all there, the basic part is we should know the equilibrium. If we know the equilibrium, then only we can proceed further. So this is a place where thermodynamics is useful. Yeah, this adsorption, desorption also we had a look. Okay, so this was all about this vapor liquid equilibrium. So what we did basically today, just give me a minute, I'm sorry. Yes, so today what we did, we started with the fact that if we know, we can find out unknown properties from known properties. If we know this Gibbs-Duhem equation, we can also check the consistency of thermodynamic data. Then we have used this slope method. X1 ln gamma 1 by x1 d ln gamma 1 by dx1 is equal to minus of x2 d ln gamma 2 by dx1. So slope should be opposite. Correct, slope should be opposite, and if ln gamma 1 is exhibiting maxima at one concentration, it should exhibit minima at the same concentration. That is very important point. But this testing is not always easy, because at each points to find out slope is difficult, and further experimental data points may not always form a very good line. It may form some scattered points, so it is not always easy to find out the slope. So there is one other better method that is proposed by Redlick and Kister, and also proposed by Harrington. They proposed it independently, and they find that if we plot difference, if we calculate the area of ln gamma 1 by gamma 2 versus x1, that should sum up to the 0. If that is the 0 at constant temperature pressure, we can say that our data is thermodynamically consistent with some limit that is less than equal to 0.0 to this area. Area below above x minus area below x divided by area above x plus area below x should be less than is equal to 0.02. Then we have various curves that ln gamma 1 by gamma 2 versus x1. In one place it follows a straight line, then in other place it follows some kind of curves, and there is one more point where it follows this kind of complex curve. Okay, so that can be correlated with Redlich-Kister equation. Okay, then we had a look at partial and completely immiscible liquid mixtures. Correct, we had that VLL diagram for two cases where we have two liquid phases, equilibrium, homogeneous or heterogeneous, then liquid vapor and pure vapor phase. When two phases are completely immiscible, we only see LV, L1V, L2V, and L1 plus L2 and V phases present. And then we had a look at these various operations where these concepts are directly used: distillation, absorption, or stripping, then extraction, adsorption, or leaching. These kind of operations, we have seen distillation is liquid vapor equilibrium, where minimum two components are required, and absorption is gas liquid, leaching is solid liquid, then extraction is liquid liquid. Similarly, when we are dealing with gas phase, generally concentration is expressed in terms of partial pressures. Then stripping, it is also gas liquid, and adsorption, it can be solid gas or solid liquid. But in all these operations, the basic thing is mu I alpha should be equal to mu I beta. I forgot to mention one more thing. When we had that example that I want to absorb H2S from gas using some third solvent. So what is there? H2S is present in very little quantity in the gas phase, and it is going from gas phase to H2S in gas phase. It is going in highly very high concentration of liquid phase. So what are we basically forming? We are forming a ideal dilute solution, and we are dealing with basically absorption. So that ideal dilute solution, that is Henry's law, we need to know that when gas is present in very large quantity, and in that large quantity of gas I need some impurity to remove. Let's, that example was H2S. So H2S in very little quantity, and that is going in the liquid solvent phase. That is also, solvent is in high quantity, and that H2S will be in very little quantity. So in this case, what do we need to know? We need to know the Henry's law constant for that operation. Okay, so this is what we had looked at till now. So now let's try to solve some example problems. We had completed till we have completed till 14th. So we'll start from problem number 15. Okay. Um, okay, till here we have done. So now let's try to move ahead with the more problems. So the first problem is we are at problem number 15th. Okay, so the problem 15 is estimate volume, residual enthalpy and residual entropy for an equimolar mixture of carbon dioxide and propane at 450 Kelvin and 140 bar using Lee-Kistler relation. So Lee-Kistler correlation, what is Lee-Kistler correlation? We have looked at this. So these are the equation for Lee-Kistler. HR by RTC not and HR by RTC prime we need to know. Then SR by R and SR by R not and SR by R prime we need to know. Okay, so for that, what we are supposed to find out, first we are supposed to find out is volume. So how can I find out the volume? Okay, so first we need to extract the data from the literature. So let me do that first. This data. So we have two components. One is carbon dioxide and another is propane. So let's first try to note down the properties from table. So for carbon dioxide, first carbon dioxide. Where is carbon dioxide? We first need to find out carbon dioxide from the standard tables. Okay, so this is carbon dioxide. Okay, yeah. So from here, we know that omega eccentric factor of carbon dioxide is 0.224. So omega 1 is 0.224. Then critical temperature is 304.2 Kelvin. 304.2 Kelvin. And critical pressure is 73.83 bars. 73.83 bar. Similarly, I need to find out propane and list down the properties. So propane should be in initial, yeah, here. So omega is 0.152. Omega 2 is 0.152. Then critical pressure is 369.8 Kelvin, 369.8 Kelvin, and PC2 is 42.48 bar. Okay, so what is told in the problem? We are told that equimolar mixture of carbon dioxide and propane. So Y1 is equal to Y2 is equal to 0.5. Now, when we are dealing with mixer, so we need to find out mixer properties. So we are just using simple summation rule that omega of mixer is Y1 omega 1 plus y2 omega 2. So zero point 0.5 into 0.224 plus 0.5 into 0.152. So the mixer eccentric factor is 0.188. Similarly, mixer critical temperature 0.5 into 304.2 plus 0.5 into 369.8. So mixer critical temperature is 337 Kelvin. Similarly, mixer critical pressure Y1 PC1 plus Y2 PC2. So Y1 is 0.5 into 73.83 plus 0.5 into 42.48. So we get 58.15 bar. Now to use it, to use this Lee-Kistler relation, we need to find the reduced property. So reduced property is T reduced of mixture is equal to T divided by Tc of mixture. So what is temperature of the system? It is 450 Kelvin. So 450 divided by 337, which is 1.335, and for critical reduced pressure of mixture. So we have mixture of pressure, pressure of mixture that is 140 bar. So 140 divided by 58.15. So that is 2.41. So we have TR and PR. So what can I find out? So let's try to have a look here. So we have TR and PR. So I can find out first Z, and from Z I can find out molar volume. Correct. So TR, what are our values? Our values are TR is equal to 1.335, PR is equal to 2.41. So first we need to find TR is equal to, okay, from here. So first PR is equal to 2.41 we need. Okay, so here, let's say approximately here PR is equal to 2 and TR is equal to, PR is equal to 2.5 and TR is equal to 1.3. TR is equal to 1.3, sorry, here. So we'll have something similar between 0.698 and 0.634 if we extrapolate the data. So we are just writing 0.697 here. If we extrapolate it, then it is 0.697, and similarly Z prime for this 1.335 and 2.41, we need to also find Z prime. Sorry, what was that? 1. PR is 2.41 and 1.3. So it should be something 0.199, something similar values 0.201. Okay, so I have Z naught, I have Z prime, and I have omega of mixer. So what can I do? I can write Z is equal to Z naught plus omega into Z prime. So I have mixer compressibility factor as 0.736. And from there, Vm is Zm into R into T by P. So 0.736 into R is 83.14, temperature 450, pressure 140 bar. So mixer volume is 196.7 Kelvin. So similarly, can we also use this mixing rule for Z? But we don't have, we will have Z critical, not, yeah, we will have to find Z because we don't have critical. We have Z, C not Z mixed, Z pure. Yeah, we cannot do it. Okay. Now, further, we need to find reduced enthalpy and reduced entropy. So for reduced enthalpy and reduced entropy, we have these plots. Yeah, this HR naught by RTC at PR is equal to 2.4 and TR is equal to 1.33. It is something minus 1.56. So we need to make some approximations. So 1 minus 1.73, you need to just do extrapolation, interpolation, and from there you can find it. Similarly, HR by RTC prime from here, it should be something similar to minus 0.178. So minus 0.169. And then from Lee-Kistler relation, HR by RTC is equal to HR naught, HR by RTC naught plus omega mixer into HR by RTC prime. So if I do this, minus 1.730 plus omega mixer was 0.188 into minus 0.169, I get minus 1.762 HR by RTC. So R is 8.314 or 83.14 based on the units, and TC mixer is this we have already found 337. So I get HR, a residual enthalpy of mixture is minus 4937 joules per mole. Similarly, if I do this for entropy, so entropy tables are also available in the literature. Yeah, see here something here similar to here, and 1.33 is here, so minus 0.891, something similar to minus 0.891, and SR by R. This term, so it is minus 0.3 something, minus 0.33. Okay, so based on that, mixture entropy, residual mixture entropy is minus 8.56 joules per mole Kelvin. Okay. So this problem, this teaches us how should we use this kind of Lee-Kistler tables available in the literature. Okay, so you can find these tables in any standard books, generalized Lee-Kistler correlation tables. Similarly, phi, when we are willing to find out the fugacity coefficients, therefore that case also we can use this kind of tables. Okay, so this was the application of using Lee-Kessler generalized table and Lee-Kessler relations we have studied in our class. Okay. Okay, now let's try to move ahead. So we have also studied partial molar properties. So the problem is based on that. The need arises in a laboratory for 2000 centimeter cube of an antifreeze solution consisting of 30 mole percent methanol in water. So we have 30 mole percent methanol, 70 mole percent water, which is consisting 2000 centimeter cube of volume solution. What volume of pure methanol and of pure water at 25 degrees Celsius must be mixed to form 2000 centimeter cube of antifreeze also at 25 degree Celsius. Okay, so I have I want to form a 2000 centimeter cube of volume that contains 30 mole percent of methanol. So what amount of pure methanol and pure water I should take? So for that we are given some data partial molar volumes for methanol and water in 30 mole percent methanol solution and their pure species molar volume at both 25 degrees Celsius are these. So this is partial molar volume of ethanol 38.632 centimeter cube per mole and pure volume at 25 degrees Celsius it is 40.727. Similarly for water partial molar volume is 17.17.765 centimeter cube per mole and water it is 18.068. So what quantity I should take, what volumes I should take such that it forms the total volume 2000 centimeter cube with 30 mole percent of methanol in water. Okay. So we know that x1 is equal to, I'm saying methanol 1 and water 2. So x1 is equal to 0.3 and total volume V total is 2000 centimeter cube and V1 bar, V2 bar, V1, V2 is given to us. So what we know that um, V is equal to x1 V1 bar plus x2 V2 bar. So x1 is zero point 0.3 into V1 bar 38.632 plus zero point 0.7 into 17.765 centimeter cube per mole. So I have molar volume of centimeter cube per mole. Now this is per mole. So I need to find total number of individual number of moles. So total number of moles will be 2000 volume we need to form divide by this volume 24.025. So we have total 83.246 moles. Okay. Now 83.246 moles and we have mole percent, 30% and 70%. So if we multiply this individually 30 and 70, we get individual moles that is required. So individually we require 24.974 moles of methanol and zero point 0.7 into that that is 58.272 moles of methanol. Correct. Water, sorry. So now if I multiply this number with pure component volumes, then I can get what is the volume that will form and it will. So what we did first, we know that when I am adding one droplet of water into large quantity of methanol, the volume change is not 18 cc per cube, but it is something 14 cc per cube. Okay, so that concept is used here. That based on partial molar volumes given to us, we can find out the volumes that is formed centimeter cube per mole. From that we can find the total moles and from total moles we can find out the individual moles and from individual moles when we multiply it with pure volume so we can find out the pure volume required for each component. So if I sum it up here, so it is not exactly 2000 but it is greater than 2000. So when I am adding 1017 centimeter cube of methanol and I am adding 1053 centimeter cube of When I am adding 1053 centimeter cube of water, then it will form a solution of 2000 centimeter cube. Okay, so this is the application of partial molar properties that we studied in the lectures. Okay, so let's try to go through it again. That we need to form 2000 centimeter cube of some volume that contains 30 mole percent of methanol. So we know at 30% concentration of methanol and 70% concentration of water, we know this partial molar volumes V1 bar, V2 bar, and V1, V2. That is something we know. So what we did, we find out from the summation rule, the volumes per mole we find out. Then we required 2000 centimeter cube. So we divided 2000, we did 2000 by this. So we found out the individual number of total number of moles required. Then based on mole concentration 30 and 70, we found out the individual moles, and from individual moles we find out the individual volume required to form the solution of 2000 centimeter cube that contains 30% of methanol. Okay, so you see that there is a slight difference in volume. So this slight difference is causing the huge difference at the end. Okay. Okay. Okay, now let's try to move it. This is very, not very, but slightly complex problem. Okay, the problem says that the enthalpy of a binary liquid system of species 1 and species 2 at fixed temperature and pressure is represented by this equation. H is equal to 400x1 plus 600x2 plus x1x2 into 40x1 plus 20x2, where H is in joules per mole. So we are supposed to find out expression for H1 bar and H2 bar as a functions of x1. Numerical values for pure species enthalpies H1 and H2, and numerical values for partial molar enthalpies at infinite dilution. So what we are supposed to find out? We are supposed to find out partial molar enthalpy H1 bar, H2 bar, then pure enthalpies H1, H2, and infinite dilution enthalpies H1 bar infinite and H2 bar infinite. Okay, so how do we do it? So we have, and we are supposed to find out everything in terms of x1. So let's try to first convert equation in terms of x1. So we have this equation, H is equal to 400 times x1 plus 600 times x2 plus x1 x2 into 40 x1 plus 20 x2. Now what I will do, I will replace x2 with 1 minus x1. Here also x2 with 1 minus x1 and x2 with 1 minus x1. Okay, so this is 400 x1. This is 600 into 1 minus x1. So 600 minus 600 x1 plus this term I have splitted it like 40 x1 square x2. So 40 x1 square x2 is 1 minus x1. So 40 into x1 square minus 40 into x1 cube plus 20 x1 x2 square. So 20 x1 into x2 square, 1 minus x1 whole square, 1 minus x1 square is 1 minus 2 x1 plus x21 square. So 20 x1 minus 40 x1 square plus 20 into x1 cube. So we have enthalpy H as 600. So if I sum it up everything, so I am left with 600 minus 180 x1 minus 20 into x1 cube. Okay, so dH by, if I now differentiate this equation with respect to x1. So what is this H1 bar? H1 bar partial molar enthalpy can be given as H1 bar is equal to H plus x2 dH dx1, and H2 bar is equal to H minus x1 dH dx1. So what do I need to find out? I need to find out how H varies with x1. So my expression for H is 600 minus 180 x1 minus 20 x1 cube. So dH by dx1 will be equal to this term differentiating with respect to x1 is 0. This term is minus 180 and this term is minus 20 into x1 cube is 3 into x1 square. So 60 x1 square. So if I put everything here, so H1 bar is equal to H plus x2 dH dx1. So H 600 minus 180 into x1 minus 20 into x1 cube plus x2 is 1 minus x1. dH dx1 is minus 180 minus 60 x1 square. So it is this term as it is, and this if we expand, so this is minus 180 minus 60 x1 square plus 180 x1 plus 60 x1 cube. So we will have h1 bar is equal to 420 minus 60 x1 square plus 40 into x1 cube. Sorry. Similarly, how can I find out h2 bar? So h2 bar is h minus x1 dh dx1. So h is this term 600 minus 180 x1 minus 20 into x1 cube minus x1 into dh dx1, that is coming out to be minus 180 minus 60 x1 square. So if I expand it, I get h2 bar is 600 plus 40 x1 cube. Now I'm supposed to find out infinite h1 bar infinite, h2 bar infinite. What does h1 bar infinite mean? H1 bar infinite meaning when x1 is tending to 0. So in this equation, when x1 is tending to 0, what do I get? I get h1 bar is equal to h4 bar infinite. Here I should have written infinite. So H1 bar infinite as 420 joules per mole. And similarly, I have this formula H2 bar is equal to H minus X1 dH dx1. So when I put values and when do I get H2 bar infinite? H2 bar infinite meaning X2 tends to 0. And what does X2 tends to 0? X2 tends to 0 meaning X1 is tending to 1. So if I put 1 here, I get 640 joules per mole. So this is how I can find out H1 bar, H2 bar, H1 bar infinite and H2 bar infinite. Okay, this problem is also there, but it is going to be slightly long. Okay, let's try to do it. So the problem statement is, if the molar density of binary mixture is given by the empirical expression, rho is equal to A naught plus A1 x1 plus A1 A2 x1 square. So find out V1 bar and V2 bar. Okay. So what is rho? What is V? V is inverse of rho. We are just saying that it is per gram, so we are not multiplying it with some number m or n. So we are just taking v is equal to 1 by rho. So 1 upon a0 plus a1 x1 plus a2 x1 square. So now to find out v1 bar, I need v1 bar is equal to v plus x2 dv dx1. So I need to find out dv dx1. So dv dx1 is 1 upon, this is minus 1 upon this whole square. Then a0 has no differentiation x1 term, so it is 0. a1 x1 differentiation will be a1. a2 x1 square, it will be 2 into a2 into x1. So it is nothing but minus of a1 plus 2 a2 x1 divided by rho square. This is rho. So rho square. Okay, so what is v1 bar? v1 bar is equal to v plus x2 dv dx1. So v is 1 by rho plus x2 1 minus x1 dv dx1. So minus a1 plus 2a2 by 2a2 x1 divided by rho square. Okay. So 1 upon rho minus this, if I expand, so this is minus I'm keeping this out. So it is a1 plus 2a2 x1 minus a1 x1 minus 2a2 x1 square divided by rho square. So I can write it down as rho by rho square, correct? So rho was a0 plus a1 x1 plus a2 x1 square minus whole this term divided by rho square. So if I simplify this, so constant term a0 minus a1, x1 terms a1 x1, a1 x1, 2a1 x1, then a1 x1, a1 x1, 2a1 x1, then minus 2a2 x1, then a2 x1 square, 2a2 x1 square, it is 3a2 x1 square divided by rho square. So it is a0 minus a1 plus 2x1, a0 minus a1 plus 2x1, a1 minus a2 plus 3a2 x1 square divided by rho square, that is a0 plus a1 x1 plus a2 x1 square whole square. Okay, so this is my v1, but this looks very complex, but it is just the concepts if you know, and it is just maths, the math that you need to solve. Similarly, v2 bar is equal to v minus x1 dv dx1. V is 1 by rho minus x1, and dv dx1 was this negative term, so negative becomes positive, so plus a1 plus 2a2 x1 divided by rho square. So here again rho by rho square I can write it down. So a0 plus a1 x1 plus a2 x1 square plus a1 x1 plus 2a2 x1 square divided by rho square, that is a0 plus a1 x here it is 1 a1 x1 plus a2 x1 square whole square. So v2 bar will be a0 first term, then a1 x1 a1 x1 2 a1 x1 and 2 a2 x1 square a2 x1 square, it is 3 a2 x1 square divided by a0 plus a1 x1 plus a2 x1 square whole square. So this is how we can find out partial molar volumes. And if I want to find out what is it as infinite term, so v1 bar infinite, what do I get? When do I get v1 bar infinite? When x1 tends to 0. So if I put x1 tends to 0, this term goes out, this term goes out, and this goes out. So what I am left with, a0 minus a1 divided by a0 square. That will be my v1 bar infinite. This 0, this 0, these two terms 0. So I am denominator, it is just a0 square. Numerator, it is a0 minus a1. So it is a0 minus a1 divided by a0 square. Similarly, what will be my v2 bar infinite? We need to put here 1 1. So it is a0 plus 2a1 plus 3a2 divided by a0 plus a1 plus a2 whole square. So this will be my v2 bar infinite. Okay, so this is all about today's lecture. We have so many problems remaining to solve, so that we'll do in next class. Okay, so those who are watching YouTube, if you have any query, please feel free to write me on this particular email ID. I will try to respond to the particular query as soon as I can. So thank you so much. We will meet in next class.